just a few centimeters.
You stand corrected. You will have another chance to ask Ralph something if you like, because as you can see, my first slide is also connected to this topic. So first of all, thanks to all the organizers for the invitation that went to the four of us here. I'm going to talk about a project that we are researching on, which is loosely called New Physics Searches in Cosmic Ray Showers. And this is a collaboration between myself, Ralph, who just spoke, Maximilian, who is doing his PhD in Karlsruhe, and a new project student called Marius Bertrand. And yeah, let's see what this is all about. So the stage for my talk, contrary to most other talks that I'm giving, are cosmic rays. So as we move to astrophysics, here is a nice overview what the spectrum of cosmic rays looks like. And it is from a very recent publication, so you can find the details in here. The interesting things for us to know, so this is the black line is from an empirical fit, and then there's a lot of data from various experiments, as you can see here in all kinds of colors. And first of all, for those of us who are used to high energy physics or particle physics laboratory experiments, is the energy scale. So here you see the kinetic energy of the cosmic ray shower in GeV. So you can see it's 10 to the 6, 10 to the 7 GeV is enormous. So these energies of this is the cosmic ray primary that hits the atmosphere, is really gigantic. But the center of mass energy is written up here. So this depends, of course, on the scattering partner of this cosmic ray primary. So it might scatter off a nucleon in the atmosphere, or maybe even a molecule or something like that. And depending on this partner, we have a center of mass energy that can be here is the LHC is 10 to the 4 something GeV. And you can see that the cosmic ray spectrum extends far beyond that. So this means we have energies in the cosmic ray collisions with the atmosphere that supersedes the energy scale of the LHC, and as a matter of fact, also that of future planned collider experiments. So I think the future Circular Hadron Collider would be somewhere here. And on top of that, these fluxes happen all the time. So they are ubiquitous, they are there, and we don't have to pay for them. We just have to collect the data, which is of course not trivial by itself. Okay. So this is what I mean by this bullet point here. They provide an untapped source for high energy physics interactions. So how to do this, how to analyze new physics in such cosmic rays is of course not very simple. So for us on the theoretical or phenomenological side, we need a tool. The one that we are using here, and I'm using only very few words, is called QuasiCAT. There is an organigram, if you wish, or showing the modular structure of QuasiCAT. I'm not going to discuss this. Here's an output of a cosmic ray shower with some particles and tracks that go through the atmosphere. So this is the height basically, and this thing comes at an angle hitting the atmosphere. If you want some details, there's a link to a talk given by Ralph a few days ago, from which I stole these pictures. So this QuasiCAT is a new framework, reasonably new framework to investigate particle physics, particle cascades in astroparticle physics. So it's meant to replace the existing ones, and it's used by many collaborations that many of us know. It's an open source and joint community project with its own GitLab directory. This is very important because it makes it transparent, and it's also very flexible. And also because it's highly modular and flexible, you can implement various geometries and also physics into this into the program structure. Here I put in brackets only Pythia 8, which is important for what I'm going to talk about in a few slides. So this means that this is it's like it's not a skeleton, but to me it is like a skeleton where I, as a theorist or phenomenologist, can put my preferred new physics in, and then we can see what impact it has on cosmic ray cascades, and then we have to figure out how to observe that. More about that later. So here's something in passing, a question that we asked while Ralph, me and Max were talking about this project, about interactions of mesons from cosmic rays, because we have literally a huge flux in every single cosmic ray collision event of mesons that are born from this event, that develop this cascade, and they pass through the atmosphere, and they also scatter. And this is the number of all the interactions that you can see for a single cosmic ray with an energy that's quite high, 10 to the 18.5 electron volt. And it was created also with numerical simulation. And then here we folded that, or actually Max did, fold this flux from a single cosmic ray with the cosmic shower spectrum that we saw in the first slide of this talk, to give you the absolute number of high energy meson interactions with the atmosphere from cosmic rays. So we can in principle integrate over the energy scale and the surface of your detectors and everything, and then you know how many interactions you have of mesons with air molecules or stuff in the air. And this is very interesting to know because you might have new physics in mind that lives on the low energy scale where mesons interact, and in rare cases, new things can emerge, and this could be really interesting. So anyhow, this was just a question that we asked on the sideline, and it was fairly easy for Max to realize. So the motivation for us to get talking is something that not many of us might know. This is the so-called muon deficit problem, sometimes also called the muon excess problem in cosmic rays or astrophysics. So we see here also from this recent paper, astrophysics paper, these are for different models being simulated, data of astrophysics showers measured on the ground. They measure an observable called Z, which I cut off here, which relates to the muon density at the ground level. So Max and Ralph are listening. They can correct me anytime I say something stupid. So these observables basically tell you how many muons you expect at the ground level, and the dashed line is the prediction from various models. So in each panel, it's a different model that has been used, and the colored dots are measurements. And you can see that for lower energies, this is quite a good match, but at high energies, we tend to measure too many muons on the ground level compared with the prediction. So the deficit relates to the prediction. The prediction undershoots the measured muon intensity or density at the ground level. And this is called the muon deficit problem. It's huge. In sigma, I don't know the updated number, but it's significant, well beyond 5 sigma, and it's not understood. So it could be could have many reasons, of course. But we ask ourselves, could this be physics beyond the standard model? Well, put it beyond in parentheses, and you will see in a second why this is. So here's the hypothesis for a new process. So if this is a new process that leads to this apparent enhancement of the muon flux at ground level, then it should become operative at a threshold energy. So maybe 100 PeV or something like that. So maybe somewhere here, okay? So this means for energies above the threshold, we have an enhancement, and for energies below the threshold, so here like the black dots, we don't have an enhancement. So this new process comes in at higher energy, and this process, whatever it might be, has to produce ultimately large number of muons at the ground level. So this means, I should say, astrophysics processes take place like 10 to 20 kilometers above the ground level. So the shower has time to evolve before it hits the ground and the detectors there. This is a very important statement for particle physicists used to high energy physics experiments like the LHC. Muons and astrophysics processes stem from decaying hadrons, and they have plenty of time to decay before they reach the ground. So in practice, we need anything that makes a lot of particles, in particular hadrons. It doesn't have to be muons. And the cross-section, that's an important point. That's point number 3 for this hypothesis. The cross-section has to be large. It has to be really comparable to the hadronic interaction cross-section. Otherwise, it wouldn't be ubiquitous in cosmic rays as it seems to be. So the hypothesis that we adopted was so-called large multiplicity scattering. And I will outline this here in the next slide. So this is on the theory of large multiplicity scattering. Let's first look at this Feynman diagram. So this is, as you can see, this looks like a LHC scattering, but it doesn't have to be. It essentially could be partons. They collide, they form a boson, which is labeled B, and this boson then decays into a large number of n bosons. Bosons could be Higgs or vector bosons or anything else. This has been discussed by Michael Spanowski and company in several papers, and they call it Higgsplosion and consider the Higgs boson. And the interesting thing is, when n is much larger than 1, then the amplitude has an exponential growth. And this means also the cross-section starts growing exponentially. And it was proposed as a solution of the hierarchy problem, and is in principle testable at the LHC and other colliders, although in practice has been studied even in some simulation. So in practice, however, the maximum number of, let's say, Higgs bosons that you can produce, let's say at the LHC and also at the FCCHH is limited by the center of mass energy. So we cannot produce many more than a few hundred of them. And this also limits the cross-section, which has to be estimated to be of order of attobarn for these collider experiments. But it's clear that if we can produce many more numbers of Higgs bosons as the cross-section increases, we might actually get closer to, say, the hadronic cross-section. There are some theoretical key questions, however. So the cross-section grows exponentially, as I said, but this is countered because the offshore mediator also grows in width, which counters the ultimate growth of the cross-section and retains unitarity. So that means we cannot have an ultimate or never receding growth of the cross-section. This means that in practice that there must be some threshold energy at which this kind of levels out and maybe becomes flat, or maybe there's a peak and it goes down again. It depends on the exact width. It's difficult if not impossible, to calculate this analytically. Many people have tried. I'm not one of them, I must say. So the question is, what is the maximum value of the threshold energy and also of the cross-section? If the cross-section is very small compared to the hadronic cross-section, then only very few of the astrophysics showers would give you observable events, like it's 1 in a million or 1 in a billion maybe, or even less. We could still be lucky and see one, for instance, in Pierre Auger, but in general, they would be very rare, and we should count ourselves lucky if we can find one. But it could be that this large multiplicity scattering cross-section is much bigger than a hadronic cross-section, or at least comparable. Then it could be the dominant process for energies above this threshold. And this would serve to explain this muon deficit problem. We take in our work diagnostic approach. So we say we don't know this cross-section, we rather constrain it. So we want to study this process and its observables that can capable of constraining or detecting and differentiating this process from the background or from the standard model induced showers. And if we find such observables, that we can determine statistically or maybe even event by event if these things, how many of these things we have in the data, then we can constrain the cross section and also model parameters. So this is what the phenomenologist would do. This is what we are trying to do. So here's the model. This is a pragmatic parameterization. We have 3 parameters, namely f, epsilon, and b. F, the parameter f, determines the amount of energy, of the fraction of energy of the center of mass energy of the given process, from which we can create the bosons and pairs. And that's loosely something, you can think of this maybe like the PDF Bjorken X, but not exactly so. So this is purely phenomenological, just to parameterize it, but not the whole energy of the cosmic ray, which could be a proton or maybe even iron, will be available in a center of mass collision. So this is what we use to parameterize F with. Then we have the parameter epsilon, which parameterizes the kinetic energy of each of these bosons that are being produced. For practical purposes, we produce them in pairs, which are produced back by back. And the kinetic energy is just distributed among the pairs. So it's while the number is fixed, the actual energy, kinetic energy that each pair gets is not fixed. It's distributed with a direct light distribution, but it's technical detail I will ignore for the moment. So is there a question? Okay. So here's the number of pairs is then given by this formula. So the more kinetic energy, can you please mute yourselves if you don't want to ask a question? Thank you. So the kinetic energy is not available in terms of making kinetic pairs, and F determines how much energy we have from the center of mass. So this formula is fairly obvious. So we assume that the bosons are being produced isotropic in the center of mass system, and then we add them to let's say to that which we call which Max and Ralph call the stack of QuasiCAT. So the particles are being produced and put in the stack, and we bookkeep the 4 vectors and everything, and then they're being handed to PCA8 and they will decay in the standard ways, and then the decay products will be evolved along with everything else via, for instance, CONEX, or maybe even with this QGS jet and your QMD algorithms, and experts know more about this one than I do. And all of this is implemented in QuasiCAT. So the new thing is that we have now process with 3 parameters, where this is actually not really a parameter, but just a choice, which boson we want to consider. And this allows us to simulate cosmic ray interactions that lead to huge multiplicity creations of bosons at the first interaction point. So at first, we only considered for the bosons the Higgs, as I said. So Michael Spanowski and company might call this the explosion. And there are some results. So this is kinematic. So I'll walk you through this. So the first 2 panels are 2 standard model showers. So you can see the shower energy. If you can, it's very small. It's 5 times 10 to the 18 electron volt. So this is a fairly high energetic shower. And we can see here in the colors the different particles that have been produced. The most prominent one is the pi 0, which was selected because we will see later on it drives the electromagnetic energy of the shower. Here's the energy of these pi zeros, and it's kind of as expected. We have like many more particles with much lower energy because the shower kind of fans out and the particles slow down as they interact with the atmosphere electromagnetically and otherwise. So we have a few events at the highest energies and the most of them later on. Similar for the gammas, the photons are also being produced from the pi zeros. So it's kind of clear that they are a little bit less prevalent, at least early on. And as I should say, this kinematics is a snapshot a few centimeters after the first scattering takes place. And what's also interesting, we see we have almost no electrons and even less muons in this standard model shower. And in fact, this is statistics limited. As we can see, this is at slightly higher energies, also standard model shower. The picture looks more or less identical. The high energy edge of the pi zero is a little bit higher. You can see here we get to slightly higher energies in the pi zeros, which is clear because the shower has higher energy to begin with. Now here we have two panels that show the situation for the large multiplicity scattering for two different values of F, which indicates how much of the energy has been used to convert into Higgs particles. And we can see quite a drastic change as expected. So we have quite a different shape in terms of the pi zeros. We have more of them at lower energies, which could stem from the fact that Higgs bosons decay mostly hadronically. And we have also a similar shape towards the high end of the spectrum, but it seems that the pi zero gets a little bit rounded down, so it has more difficulty to reach the higher energy of the shower itself, which is interesting. So here we have F being 0.2. Here we have F being equal 0.8. So we use more energy to create Higgs bosons instead of kinetic energy width. And this pushes the upper end of the energy of the pi zeros a little bit to lower values. And the most interesting thing is maybe now we see in terms of electrons and muons, we have a lot more of them. This is something that's almost absent in the upper panels in the Standard Model, but we produce huge numbers of electrons and muons at fairly high energies. You can see here 10 to the 7 GeVs, fairly high. And in particular, the electrons cannot be expected to, the electrons might actually disperse away from interactions, but the muons would probably reach the ground level. This lets us expect what to see in a few slides. So let's have a look at the first observable that I want to share with you, so which is called XMAX, which is the shower maximum of the electromagnetic shower. So the visible light, or visible quote unquote of the shower as it evolves in the atmosphere. And this is obtained from simulation, which Max actually already reported at last year's ICHAP. And I don't want to say too much, but there's the characteristic shower depth relates to the energy of each astrophysics shower event, and can be used to kind of infer its energy and also what the primaries used to be if you have standard model process as an underlying assumption. And the sigma here is the variance of this Xmax value. Okay. Now on the next slide we see how this Xmax looks in the presence of a explosion or large multiplicity event. So here we show the lines here show the different colors show different values for epsilon. In this left panel we keep F fixed. Sorry, F is indicated by the axis here, and this is the shower depth. So first of all, we know that if F goes to 0, we create 0 Higgs particles in the first scattering, and then we get back to the value that we saw earlier, which is like 800, which is a standard model process. So this is as expected. And as F increases, this is something that we saw here. The pi zeros, which drive the shower most of all, are being pushed to lower values, also as expected. And as epsilon increases, we can also see that the shower depth again increases, which also kind of makes sense because the decay products from the Higgs bosons will have higher energies. And then this is the variance, and I don't know if there's much to talk about that. Leave it just that note that if F goes to 0, this also kind of goes back to what a standard model would produce. So this seems to be consistent with standard model predictions in the limit of F going to 0. Okay, so at this point, I want to add that we don't really know anything about F and epsilon. They're free parameters, and we will discriminate them later by confrontation with data, which hasn't happened yet. And here's maybe the more interesting observable, or not more interesting, but very interesting because it connects to the starting point. This is the muon spectrum at ground level. So here we have the number of muons as a fraction of the energy. So it goes down. So in black, you see like this is a standard model process, or let's say standard shower. This comes from simulating many events, and the variance has been included. And for very low energies, most of these events come from interactions of particles with the atmosphere. Therefore, it behaves as in the standard model. But the higher energies, they certainly relate to this bulge that we have seen here, which are absent in the standard model, but are definitely present in these large multiplicity scattering events. And this means ultimately that at the ground level, we get a lot more muons, especially at higher energies. And the scaling with F and epsilon is more or less as expected. So now, before I conclude, I want to give you a short outlook. So this, as I said, this is work in progress. We want to still compare with data. We want to discuss other bosons. We've started with that already, namely the Z and W bosons. But there are many other interesting observables besides the ones that I showed you. For instance, high energy lepton bundles. So in other words, the spatial distribution of the leptons that we produce in the first event. And we can look at other detectors, namely IceCube, Atlas, CMS, Decor, and of course, in principle, every large-scale detector can be interesting because when they have downtime and they're not being fed with particle beams, they can actually be used, and they are being used for astrophysics observations. And then there's one more thing which is interesting to think about, which is the ongoing Anita excesses. So this is the last of these publications. I'm not sure if you followed up on this one. This has been just a few months ago, and this was the 4th flight, and they observed yet another couple of 2 events that seem to be coming through the ground. And recently also IceCube has made a statement that the astrophysical explanation under the standard model hypothesis is disfavored. This was very recently, and but still based on Anita 3 flight data. So I think this is a very interesting setup, and I tell you why on this slide. So this is not only my own idea. Many people have worked on this already, and some papers you can see later on. You can imagine that new physics is born in cosmic ray interaction with air in a rare process, producing a long-lived particle penetrating the Earth, which neutrinos, for instance, cannot at this energy, and then at a later stage, after the Earth basically decaying into something or interacting with the Anita detector. And there are some explanations that involve TV scale resonances, long-lived particles, and IceCube makes compatible observations that could explain these upgoing Earth emergent IceCube observations from like 2 or 3 years ago. And this should, if this is really a physics phenomenon that's related to something that happens in cosmic ray interactions with the air, this should be visible in really many, and if not all, large-scale experiments. And this should be globally analyzed. And the prototype that I could think of is really that you have, like, if you imagine cosmic ray hits an air molecule, red could indicate hadronic or hadrons that are being produced in the process. Then at some point, this could be like a pi0 decaying into this one might be something like a photon. It could decay into photon and the long-lived particle, which could be dark photon or whatnot, and that could then do the job for us on the other side of the Earth. If the energy is enormous, then it will easily have long lifetimes to get to the other side, and also the energy of its decay products will be sufficient to trigger Anita and IceCube. So the good thing about this is that these fluxes are everywhere; they're ubiquitous, and let's see if I missed any of the bullet points. Yes, so this has to be considered over all energies and angles, and we don't need to build new detectors for this because every single detector in the world will be able to see something like that. This could mean something for the recent xenon result, which I haven't included here. And just as a last concluding or summarizing slide for this little outlook, a few of the existing works that are dealing with comparable situations, this I like because it's very recent, and Bhupal and company have worked on several explanations for these things. And so this is just one example, but you can really combine models that connect to neutrino masses and also lepton flavor anomalies and new physics, leptoquarks, whatever, with these things. So this is really interesting. Basically, every long-lived particle that you can imagine should have a role in there. And with this, I want to conclude. So the cosmic rays constitute an ubiquitous source for BSM searches, but we can search for resonance at super LHC energies, which is very challenging and not clear how this can possibly work. But this is to be seen with the right tools. Long-lived particles, in particular, if they can be produced from meson decays, can be really also complementary in a complementary way studied. So there is a complementarity. There's a feedback. Thank you. So the one point here is very important. So there's a link between cosmic ray simulation and BSM model, which is not really existing, but that's something that we are working on with QuasiCAT. And so yeah, we will keep you updated on that one. And of course, signatures in cosmic ray showers is something that's not widely studied. There have been some previous studies also from Michael Spanovsky and company, and also some others, but there is still room for improvement. And I think this is very useful to study existing anomalies, and there's a lot of discovery potential. And that's all I want to say for now.
Thanks a lot, Oliver, for this very informative talk. So now we have time for some urgent questions. Also not so urgent ones, maybe.
Maybe a question. Nice talk, Oliver. This is David. You didn't mention sphalerons, but this is probably one of the first possibilities that was considered to explain the cosmic, the excess of muons.
Yeah, that's a good point. So I'm not sure if they can deal with the excess of muons. Maybe they can, but this has been studied, not in this context, but sphalerons and cosmic rays. So it's in an commented out item point here. So I updated this recently, but I think it's like 3 or 4 years ago, by some Asian colleagues, and it was a good article, and they considered sphalerons and also black holes, I think. Maybe Max remembers more details about that one. These analyses exist, but as I said, so the important thing is really the simulation, as we all agree. If you deal with complicated detector, but also physics processes, you need to, in order to quantify something, you need a realistic simulation setup. This is why we have all the suite for LHC and companions, all the simulation software, and this doesn't really exist. not for BSM. For the standard processes, the suite exists, of course, for astrophysics, but we need something comparable to the LHC, like MatGraph and the Delphis and company. Something that this is really missing, and if this is there, this can be studied in all depth. I agree. So sphalerons are one candidate. They should be there. How relevant they are, I cannot say. My feeling is they produce too few muons. They do produce more, I guess, than a standard model, but I don't think enough. But we didn't study this in detail.
Thank you.
Okay, are there more questions for Oliver?
I have a technical one if there is time, but I understand. So Corsica 8 in principle is motivated just to be a C++ version of Corsica, right? So the fact that now it handles BSM signals is something that could be done also with Corsica. Is something that could a plugin could be inserted in Corsica.
So if I understand, so Ralf and Max are, I think, in the audience, so they can also comment, but let me try to do it first.
Yeah.
If I understand your questions correctly, then, sorry, yeah, thank you. So the idea is, so Corsica will not be modified by itself. Ideally, we would use a plugin, like an existing Monte Carlo simulation framework, maybe. Maybe there is a way to make this a bit simpler, because not all the kinematics are just as interesting as the LHC, but you could visualize or envision to use let's say a MatGraph interface with Corsica 8 and then run it. Pythia is already working. This is interfaced with the Corsica flow, as you can. I think you can. It's probably in the physics here, and Pythia can already be modified by hand to include new physics. So I think. Yeah, what we need are
okay. Now I understand what you tried to say. So in fact, okay, the possibility to interface with other tools is what is really crucial here. That you can interface to tools that can handle BSM. Okay, thank you.
Happy.
All right.